We have covered 3 of Maxwell's 4 equations. Gauss's law for electricity, electric charges create electric fields. Gauss's law for magnetism, no magnetic monopoles. Faraday's law, changing magnetic fields create electric field. In 1820, Hans Christian Ørsted made a discovery that changed physics. During a lecture, he noticed that a compass needle moved when he brought it near a wire carrying electric current. He realized that electric current lines form circles around the wire. But we have not yet answered a fundamental question. How do we create magnetic fields in the first place? The answer comes from the 4th and final equation, Ampere's law. Here is the apparatus, a straight wire connected to a power supply. A compass sits beside the wire. The switch is open, no current. The compass points north, following Earth's magnetic field. Now I close the switch. Current flows. The compass needle swings. It is no longer pointing to Earth's north. It is aligning with the magnetic field created by the current in the wire. And the magnetic field lines are circular, so the needle points tangent to that circle. With no current, the filings lie randomly. No magnetic field, no pattern. Now I close the switch. Current flows. Watch the iron filings. They align into perfect circles around the wire. The magnetic field lines are concentric circles. This is the fingerprint of a current-carrying wire. Iron filings are tiny particles of iron that align themselves along magnetic field lines. Watch what happens when I sprinkle them around a current-carrying wire. The magnetic field created by a straight wire depends on the current. More current, stronger field. The field also depends on distance, twice as far, half the field. And it depends on a fundamental constant called the permeability of free space, mu naught. The permeability of free space, mu naught, is the value in a vacuum. But different materials have different permeabilities. Iron, for example, has a permeability about 200 times higher than free space. That is why putting an iron core inside a coil creates a much stronger magnet. The material itself amplifies the magnetic field. The direction of the circular magnetic field is given by the right-hand rule. Point your thumb in the direction of the current. Your fingers curl in the direction of the magnetic field. This rule works for any straight wire. The magnetic field around a long wire is given by this equation. B is the field strength, I is the current, and R is the distance. Notice the field decreases as we move away from the wire. So the field is proportional to current, but inversely to distance. Here is a more advanced demonstration. 2 parallel wires on precision mounts. I can control the current in each wire independently, and I can measure how much they move. When current flows in the same direction in both wires, the wires attract. The magnetic field created by one wire interacts with the current in the other wire, producing a force. The force per unit length is proportional to the product of the currents divided by the distance between them. When current flows in opposite directions, the wires repel. This is how Ampère measured the magnetic force between currents. His experiments led to the mathematical form of Ampère's law. Ampère's original law described how electric currents create magnetic fields. It says, the curl of the magnetic field at a point is proportional to the electric current density at that point. Curl from Ampère's law tells us that currents create circulating magnetic fields. Remember, curl measures rotation. Imagine a tiny paddle wheel placed in a magnetic field. If the field circulates around the wire, the paddle wheel would spin. That is curl rotation. Hence, Ampère's amount of rotation. Ampère's law says the amount of curl is proportional to the current passing through the wheel. Ampère's law worked for steady currents, but it failed for circuits with capacitors. The current appears to stop at the plates, but a magnetic field still exists. So, what creates that magnetic field? Here is a capacitor. I place a magnetic field detector, a Hall probe, between the plates. With no current flowing, the meter reads 0, no magnetic field. Now I turn on the power supply. The capacitor charges. Watch the meter, a magnetic field appears between the plates, but there is no current flowing across the gap. So what is creating this magnetic field? James Clerk Maxwell saw the problem. He realized that a changing electric field, even without a current, can create a magnetic field. He added a second term to Ampère's law. Mu naught, epsilon naught times the rate of change. This term is called the displacement current. Between the capacitor plates, the electric field is changing as the capacitor charges and discharges. That changing electric field creates a magnetic field. Even though no charges are flowing across this field, the electric field is changing fastest. The magnetic field is strongest when the electric field is changing fastest. This is Maxwell's displacement current. This is the complete Ampère-Maxwell law, the 4th of Maxwell's equations. It says there are 2 ways to create a magnetic field. First, electric currents moving charges. Second, changing electric fields even in empty space. This second term is Maxwell's genius. Here is the revolutionary consequence. Faraday's law says a changing magnetic field creates an electric field. Ampère-Maxwell says a changing electric field creates a magnetic field. Together, they describe a self-sustaining wave. The electric field creates a magnetic field, which creates an electric field, which creates a magnetic field propagating through space. Maxwell calculated this speed as found the speed of light. Light is an electromagnetic wave. Maxwell died in 1879. In 1888, Heinrich Hertz became the first person to generate and detect radio waves. He used a spark gap transmitter and a receiver across the room. No wires tapped freeze when Noel was raised. The unit of frequency, the Hertz, is named after him. Maxwell's equations revealed that the speed of light is a fundamental constant of nature, is a constant rate. This constant speed is the same for all observers, that are patterned Caliber Einstein to special relativity. Maxwell's equations enabled virtually all modern technology: radio, television, microwaves, cell phones, GPS. Every wireless device you use, every signal that travels through waves are real.
Maxwell's equations are among the most successful in all of physics. They unified the related radio waves to radio light at traces of 800,000 kilometers per second, and they set the stage for Einstein.
We have covered all four of Maxwell's equations. Gauss told us how charges create electric fields. Gauss for magnetism told us there are no magnetic monopoles. Ampère pair with Maxwell's correction showed us how changing electric fields create magnetic fields. But writing the equations is just the beginning. The real magic happens when we solve them. Next, we will explore the solutions to Maxwell's equations, the electromagnetic wave. We will see the deep symmetries hidden inside them. We will discover how these solutions give us light and everything in between. And when equations that is coming next. Stay tuned. And we will see how engineers use these solutions every day to build the technology around you. That is coming next. Stay tuned.